Welcome everyone to the Auditing Bridge Smart Contracts webinar. And today we are going to break some bridges and then fix them back. We have a full repo with real Solidity smart contracts where we are going to find vulnerabilities in. We will write exploits, run them, and then apply fixes and see the same exploits fail. This repo will be shared with you right after the session, so you can replay everything on your own machine. I am Olesia, Smart Contract Auditor at Hacken. I have more than 4 years of professional experience in smart contract auditing, and before that, I was working as a software engineer with a background and main focus on security and blockchain technologies. And here is our plan for today. Firstly, we will do a quick overview of bridge architectures. We will review what types of bridges exist and how they are built. Secondly, we will trace the life cycle of a cross-chain message from the very beginning to the minting on the destination chain. And thirdly, we will have the main part of today's session, which is common vulnerability patterns. We will audit real breach contracts and run exploits on them. And finally, we will apply fixes and run the same test to confirm that the vulnerabilities are resolved. So bridges have two main dimensions. The first is about how tokens move between chains. The most popular one is lock and mint, where tokens are locked on the source chain and minted on the destination chain. Another model is burn and mint. This is when tokens are burned on the one chain and minted on another. The second dimension is how messages are verified. Some bridges rely on validators or set of validators. Others use optimistic verification, where messages are submitted and then can be challenged during the defined time window. And some uses light clients which rely on on-chain proof verification. And in practice, each bridge combines these two dimensions. Let's look at the canonical execution of the lock and min bridge. Everything starts on the source chain. So these two steps belong to the source chain, where everything starts with user depositing, let's say, X amount of tokens to the source bridge, where those tokens are locked or burned, depending on the bridge type. Then the message with this data is constructed and hashed directly from here. Off-chain validators listen for the events and they sign the verification of these messages. Then we move to the destination chain. So these 4 steps belong to the destination chain part. Destination. So this signed message goes to the verification part, where this signature is recovered and we receive this validator who signs the message. Then it goes to the authorization part, where there is a set of validators or one validator depending on the message architecture. And it is verified whether this validator exists here, or in case there is a threshold logic, it is verified whether it is satisfied, and if everything checks, the X amount of tokens is minted or released here. And the message is marked as processed, so it can be replayed. So we have 6 steps here, and each one is a potential point of failure. This is the audit framework we will use today. So we will not just list random vulnerabilities for the bridges. We will break bridge security into 4 layers, and this framework would work for each bridge type. So the first axis is trust and authorization. This is about who is allowed to mint or release assets and how that authority is proven. This includes signature verification, validator sets, and threshold logic. The second axis is message integrity. That's about whether the signed message is exactly what gets executed. For example, whether some fields can be modified or whether the message is used in the intended context. The third is economics and invariance. This axis is very oftenly omitted in practice, but it is also fundamental. This is about whether the breach respects the project tokenomics and invariance. And the last but not least is liveness and recovery. So what happens if something goes wrong, both off-chain and on-chain? For example, if validators go offline or the breach is paused, can users still recover their funds? This is the questions which we as auditors need to ask. And for each axis, we will look at the design, demonstrate a real exploit, implement the fix, and rerun the same exploit on the fixed version. All right. Let's get into the first axis of our audit model, trust and authorization. This is the first and the most fundamental axis, because before we even can start thinking about liveness, about recovery, economics, we need to answer one question. Who is allowed to release and mint assets on this destination chain, and how do they prove their authority? Because if this layer is broken, nothing else really matters, because the breach just becomes a faucet. This is the same canonical execution pipeline which we learned here, and we need to understand which steps we need to protect in this layer. So the trust boundary sits right here in the verification and authorization step. So everything to the left should be not trusted and should be assumed as an untrusted input, and everything to the right assumes that the input is validated. So 3 questions which we need to ask during the audit. Who can authorize the release or mint? How do they prove their authorization? And what assumptions are made of chain so the contracts can't verify them? Different bridge architectures answer these questions differently. For example, validator-based types, which use N of M signatures, have the weak or forged signature as their failure mode. Oracle-based bridge types rely on price feeds. So in case the oracle is compromised, the bridge is compromised. Optimistic bridges, like Optimism, use a challenge window. So their failure mode is censorship. If challengers can be censored, invalid messages can go through. And light client bridges verify proofs on chain. So there is a verification bug in the implementation. The bridge is not secure. So let's look at the authorization flow. Here is the detailed flow. User takes an action, let's say deposit some Ethereum. The message is constructed, the hash is computed. Then on the destination chain, the signature is recovered and it is verified whether the signer belongs to the validator set. Then, if there is a threshold logic, it is verified whether it is satisfied. And if everything is fine, the message is marked as done and tokens are released or minted. Otherwise, the message is reverted. If there is no threshold logic, we skip this step and go directly from here to here or here. So this is how it should work, but let me show you how it may break. Let's go to the code. We have a real log and mint bridge here, and this is the source chain bridge. So users call deposit. They provide Ethereum and specify destination chain ID. The message is stored, the nonce is incremented, and the event is emitted. Off-chain validators listen for this event, and then we go to the destination bridge. So let's go to the destination. So here we have the bridge destination, and main logic happens here in the relay function. So it submits the relayer submits recipient, amount, nonce, and the signature. So let's trace the authorization flow step by step, just like in our diagram. If we return to it, just to remember, firstly, the message is constructed, hash is computed, and the signature is recovered. That's exactly what we see here. The message digest is created, the signer is recovered. Then we verify whether the signer is the allowed validator. If we check how this validator is set, it is set during the contract creation and can be only set by the owner. So everything is fine here. But let me scroll down to the message digest and see what the hash includes. So it includes recipient and the amount, just these two fields. So if we return to the relay function, there is a deposit nonce. It is in the message signature. It is also in the event, but actually it never enters the hash. And if we return to the message digest, we can see that there is also no block information or contract information, so no domain separation. What does it mean? Let me show you. I've prepared an exploit test. Here it is. So what we do here, Alice deposits 5 Ethereum on the destination chain. The validator signs an attestation for her, and the relayer takes the signature and submits it to the destination A. Then the relayer takes the same signature and submits it to the destination B. Let's try exploiting this. One moment. Yeah. Forge test, match contract, incomplete hash vulnerable, match test, and cross contract replay, and let's trace everything. And we see that it passes, so Alice deposited 5 Ethereum on the destination chain and received 5 wrapped Ethereum on the destination A and destination B. But it can even get worse. Let me show you. So Alice deposits 5 Ethereum again on the destination chain. Validator signs an attestation, and the relayer takes this attestation and submits it 5 times to the same destination. So let's just change the test here. and we see that it passes. So Alice deposited 5 Ethereum but received 25 wrapped Ethereum on the destination chain from a single validator signature. So the breach is totally insolvent. Let's go back to our flow and analyze. What assumption was violated here? So this is right here at the hash computed step. The hash was not complete. It didn't bind the signature to a specific chain, specific bridge instance, or a specific nonce. So the same signature was valid everywhere and forever. This is called incomplete hash pattern. No domain separation means cross contracts replay. Let's return to the code and try to fix it. So we have the same destination bridge, but if we go to the message digest, we see that it now includes a source chain ID, so the chain where the Ethereum was locked on, destination chain we are on, source bridge, current bridge, recipient, amount, and nonce. So every signature is now scoped to one source chain, one destination chain, one source bridge, one destination bridge, and one deposit. And here in the relay function, each time the nonce is used, it is set as persist, and in the start of this function, it is checked whether it has not been used before. So even if someone tries to replay it, the nonce guard should catch it. Let's return to the exploitation tests and try to run them, but on this fixed contract. So let's firstly try to submit the same signature onto different destination bridges. Now it reverts this invalid signature, so cross-contract replay is now blocked. Let's try to submit the same signature on the same contract 5 times. So we just change the contract from the vulnerable to fixed. And it is also blocked, so the fix was really straightforward, but the bug was solved. So the deposit nonce was here in the function signature. It was even in the event, but it was not in the hash. So this is the kind of the thing which is easily catched during the systematic audit. Okay. We've seen now an incomplete hash, how incomplete hash breaks domain separation. Now let's look at a different problem, message ordering. So here on the source chain, users deposit funds. Alice deposits first and receives nonce 1. Bob deposits second, receives nonce 2, and Charlie deposits the third and receives nonce 3. Validator observes these deposits and signs attestations for each of them. So we now have 3 valid signed messages. These messages are then delivered by a relayer. And relayer is usually permissionless, so anyone can submit these messages. So the relayer firstly delivers Alice message with nonce 1. Then relayer decides to skip the message with nonce 2 and submits the message with nonce 3. Let's go to the code and see what this will lead to. So we have this new bridge here. It has a last persist nonce variable, so it's tracking state. There is a stale nonce error, so it's trying to prevent replace. Let me walk you through relay function. So there is a check which requires the nonce to be fresh, and it updates last processed nonce to the one used now. But actually, what does it mean? If I, as a relayer, submit the deposit nonce 1, it works fine, and last process nonce becomes 1. Then I want to skip some messages due to various reasons, and deposit nonce is 5, and last process nonce becomes 5. So later, if I try to submit the message with deposit nonce 2, 3, or 4, this will revert because these are less than last process nonce. This is the first bug here, and if we scroll down to the message digest, we see the same bug as in the previous exercise. There is no nonce here and no domain separation. So we have two bugs working together. The relayer controls the nonce and can skip nonces. Let me now prove both. Let me show you. So what we do here is exactly what was shown on the diagram. 3 users deposit 5 Ethereum on the destination chain, and the validator signs an attestation for all 3 of them. But the relayer firstly submits the message with nonce 1, then with nonce 3, and then when the relayer tries to submit the message with nonce 2, it is reverted. Let's try running it. Forge test, match contract, incorrect ordering, and this specific test. And it passes. So Bob was not able to receive their funds, though they deposited 5 Ethereum on the destination chain. It is permanently blocked. So let's go to the second exploitation. What we see here is that Alice deposits 5 Ethereum on the destination chain, and validator signs the attestation, and relayer firstly takes this attestation and submits it with nonce 1. Then the relayer takes the same attestation and submits it with nonce 100. Let's try running it. Nonce substitution. And it passes. So Alice deposited 5 Ethereum and received 10 wrapped Ethereum on the destination chain. So the nonce was not signed, so the relayer just picked two random nonces and used the same signature twice. So here is the same thing as a data flow. Alice and Charlie, green passes, they were able to receive their minted wrapped Ethereum, and for Bob, red pass. So nonce 2 was censored, and 5 Ethereum deposited with nonce 2 stuck on source. So now we need to understand what exactly broke in the flow. So everything was good on the source chain because users were able to deposit funds there and received correct nonces. Everything also worked good on the validator side because validator signed an attestation for each of the deposit. And Also, everything was fine here on the relayer side because relayer is permissionless and Charlie, for example, doesn't need to wait until Bob submits their attestation. So the problem lies here in the destination chain implementation. The last nonce stored may mean that there is a requirement to have strict ordering. Therefore, in case strict ordering is required by business rules, this gap should not be allowed. So this transaction should not be successful before this transaction happens. Or in case the strict ordering is not needed by business rules, we should not block all the previous nonces which were not executed. So all we need to do is to track which nonces were used. Let me go to the code and show you the fix. It will have two parts, and importantly, we will not use strict ordering. And let me explain why. That's because we don't, let's imagine we have some business rules and we don't need this strict ordering. And we don't want to create a liveness problem where if one relay fails, all the next relays fail because of this. So let's go to the code, and here is how it worked before. We had this last persist nonce variable, and now we have the mapping persist nonces. And if we go to the relay function, we see that each time the nonce is used, it is marked as persist, and it is checked whether it hasn't been used before. And if we scroll down to the message digest, we also see that there is a domain data and nonce is included. Let's try running the same tests. Firstly, we want to try blocking Bob from receiving their funds on the destination chain. So this is the test we want to run, but we just change the contract to the fixed. And it fails. So we see that Bob was able to receive their funds, though their attestation was delivered after the third one. Then let's try to forge the nonce and reuse the same attestation on the same bridge. And this is substitution, but on a different contract. And it also is blocked now because we see that Alice was able to receive exactly 5 wrapped Ethereum as was deposited, not multiplied by 2 like was in our exploitation example. So to sum it up, let's wrap up this with the root cause patterns we demonstrated. So no domain separation means cross-contract replay. This is what we saw in the first breach. The hash covered recipient, it covered amount, but it didn't cover chain ID, contract address, and nonce. So one signature was valid everywhere and forever. The fix was to include full domain, source chain, destination chain, both bridges addresses, and also nonce. The second one is weak recover. We didn't demo it, but it's important to remember that using raw SC recover can accept malleable signatures. And wrong ordering is what we just saw. Gap-tolerant nonce checks let the relayer skip messages, leading to the permanent censorship. And for all of them, it's important to remember that it's always needed to include nonce into the signing data, because otherwise the relayer can reuse the same signature with any nonce value, leading to double minting. So we've seen single validator breaches, and now let's look at something closer to production and of a multisig. The idea here is simple. We don't use single validator, we need a quorum. So we may see that there is a validator set, and as soon as deposit event is observed, validators sign an attestation. The relayer takes them all, submits them as one transaction to the destination bridge. Destination bridge then recovers each signature, verifies each validator, also counts the amount of validators who signed the message, and verifies whether this threshold is satisfied. And if everything is fine, the tokens are minted and the message is marked as processed. This is how it should work. But let me show you what may happen when it is not implemented securely. So here we have the multi-sig bridge. We also use the same source bridge, but different destination bridge. This is 3 of 4 bridge, so we have validators here. We have validator count, which is 4. We have threshold, which is 3. That's stated here, 4 and 3. And if we go to the relay function, we see that there is a loop here, and per each iteration, so it iterates through the signatures provided, and during each iteration, it recovers the signer, verifies that the signer belongs to the validator set, and increments the valid count. Looks solid. If we go to the message digest, we see that it's all good here. There is a domain data, and there is nonce here. But let me show you how we can exploit it. So what we do here, validator A signs an attestation, and an attacker takes this only once signature and puts it as copies it and puts it 3 times to the same array. Then takes this array and relays it to the bridge. Forge test, match contract, duplicate signers, vulnerable, and let's trace it. So it is passed. So 3 of 4 threshold was bypassed with only one validator duplicated, one validator signature duplicated 3 times. So if the single key was compromised, the entire bridge is drained. So if we return here, we see that even though this recovering is correct, this validation is good, there is no uniqueness check. So here is what happened. The attacker compromised only validator A. They even didn't do any deposit, then copied signature 3 times and submitted them to the bridge. Bridge recovered each of the signatures, and it was correct. Count was incremented. It was 3. The threshold was 3, so it was reached. But the unique signer was 1. So the threshold was supposed to require consensus from 3 independent validators. Instead, only one validator could drain the bridge. Let me show you how to fix it. So what we do here is we change relay function and we enforce strict ordering. So we track last signer And and for each recovered signer, we check if signer is less or equal than last signer. Uh, so strictly ascending. So if the same signer appears twice, the second one is not greater than the first. This is a gas-efficient way to detect duplicates without extra storage, without no additional mappings, arrays, just ordering. Let's try run the same duplicate bypass test, but on this contract version. Fixed. So duplicate now is rejected with this signatures not sorted error, which means that 3 of 4 threshold with sorted signatures now works. So here is the fixed flow. Signatures came in as AAA, so the same signature copied 3 times. But firstly, we deduplicated them and received this unique amount of signers, which was 1. And unique, which was 1, was less than threshold, which was 3. So the transaction was rejected. The key lesson here is when we do the audit of a multi-sig breach, we need to check whether the uniqueness is enforced, because count means nothing in case duplicates are not filtered. Next trust model is Oracle-based breaches. Instead of validator set, there is a single trusted Oracle like Chainlink or any other. So a user deposits on the source chain, Oracle observes deposit event and constructs an attestation, which includes chain ID, breach, recipient, nonce amount, and timestamp. And this timestamp is a timestamp when this event was observed. When Oracle signs this attestation, it is delivered to the relayer, and relayer submits it to the destination breach. And the task of the destination breach is to recover the signature, ensure that it was signed by the trusted Oracle, so this one, to check whether this nonce was not used before, and to check the timestamp freshness. In case everything is fine, the tokens are minted and nonce is marked as done. So let's see what happens in case Oracle works fine, but destination breach doesn't implement all the necessary checks correctly. So here is the Oracle breach, which submits, so it has set Oracle, and there is a relay function. It accepts recipient, amount, deposit nonce, timestamp, and the signature. The digest is created. It includes timestamp, and it recovers the signer and verifies that the signer is a trusted Oracle. It also sets the nonce, deposit nonce as persist and verifies whether it was not used before. But let me show you what is wrong here. So what we do here is we receive the attestation from the Oracle, hold it for 1 month, and then relay to the breach. Forge test, match contract, stale attestation. And it passes. So 30-day-old Oracle attestation was accepted, and in production, this means that the attestation, which was signed in a dramatically different market condition, is now accepted. So this is not secure. So this is what happened. the oracle signs the message, attacker holds it for days, week, months, then submits it to the breach, and attestation is still valid here because there is no time limit. And the breach executes a stale attestation from a different error. Let me show you how it should be implemented. So we have the same Oracle breach here, but there is this line now here, which checks whether the timestamp received is not greater than the max attestation age, which is a constant of 1 hour. So if we try to submit this stale attestation, let's try. So now it is rejected. Now the breach enforces this require now minus timestamp less or equal than max age. So signed message, when signed message is held by attacker and then passed to be executed by the breach, in case it is stale, it is simply rejected, and only if it is fresh, it is executed. And last trust model is optimistic breaches. It's completely different from everything we've seen. There are no signatures here, no oracles, no validator set. Instead, we have a game theory here. So anyone can do a proposal of anyone can do a proposal, and proposal of a cross-chain message. The proposal starts this censorship window. Here it is 1 hour. And during this window, in case challengers believe that this proposal is fraudulent, they may challenge it. And after the challenge window is elapsed, during the execution, it is checked whether the proposal was not challenged. If it was not challenged, it is executed. Otherwise, it is reverted. Let me show you the pseudocode. Here are 3 functions here. The first is propose. It sets challenged field to false. There is a challenge function which sets proposals challenge to true, and we have an execute function. It has 3 required statements. The first is to check whether the proposal exists. The second one is to check whether it has not been executed before, and the last one checks whether the proposal the challenge window has elapsed. But as we see, this challenged field is not checked here. This means that though we can challenge, during the execution, we can execute the challenged proposal. So this is how it should happen. When we submit the message, we should wait for the challenge window, and when it is elapsed, the challenged field should be checked, and in case the message was challenged, it should be rejected, and only if it was not challenged, it can be executed. So now if we go to the fixed code, we see that there is an added field here, which checks for this field, for this challenged field. So now, in case the proposal was challenged, it can be executed. Otherwise, it works. To sum up this axis, we had 5 breach types and 5 bugs with one pattern for most of them. The gap between what was signed and what was executed. So incomplete hash led to the cross-context cross-contract replay. There was no domain separation, and signature could float between contexts. Unsigned nonce led to the censorship and nonce forgering problem. Missing the duplication of signers led to the threshold bypass in the multi-sig bridges. Missing freshness validation led to the problems in the Oracle-based bridges because stale attestations could be submitted. And unchecked challenge is for the optimistic bridges, and it allowed fraudulent messages to go through. So we've secured the trust boundary, who can authorize, and now the question is, even if the authorization is valid, can the message be fraudulent itself? Access 2 is about message integrity, making sure that what was signed on the source chain is exactly what gets executed on the destination chain and in the intended context. So the message integrity can be defined by four main properties. No replace, meaning that message can be executed only once. The right chain and the right bridge, so the message executes in the correct context. Nonce is correctly consumed, so the message cannot be reused. And domain binding, meaning that the message cannot be moved across chains or contracts. If any of these are broken, the authorization itself may be valid, the signer may be correct, but outcome can be wrong. The message integrity is compromised. Here is the same pipeline from Axis 1, but now we are looking at different steps. The failure points for message integrity is spread across the pipeline. The first is message construction. If the hash doesn't include all the execution parameters, the message is malleable. Verification. Uh, if signature recovery is weak, invalid messages may pass. And the last one, marking message as done. If replay protection is broken or weak, messages can execute twice. And if any of these fail, integrity fails. So message integrity depends on three different mechanisms working together. The first is message construction. What goes into the hash? We spent a lot of time on Axis 1 talking about this, and we saw how missing fields may lead to the cross-context replay. Verification, how is the hash is validated against the signature. For example, using raw AC recover may lead to the malleable signature going through. And replay protection, correct nonce consuming, correct ordering execution, and that's probably it. So if any of these fails, integrity fails. So we already demonstrated verification and replay in Axis 1. So in this section, we will focus on a more subtle variant of message construction, partial payload hashing. So this is the cross-clay pattern we already demonstrated live in Axis 1. So there is a signed message which misses chain ID and contract others. Therefore, it is accepted in both chain A and chain B. So we will not redemo this, but I am showing this here because it's also a message integrity failure. The message is not bound to its context. So we need just to recognize it's the same root cause, but from a bit different angle. The fix is to include chain ID and address this way. the message will be accepted in the correct context and will be rejected on the not intended context. But there is a more subtle version of this problem. What if the hash includes the domain, chain ID, bridge address, nonce, but not the full execution payload? Let me show you. Here is the message bridge. Yeah. So here is the general purpose message bridge. So in Axis 1, we used token bridges, but this one supports arbitrary execution. So relay function takes 7 parameters: nonce, token, amount, recipient, target contract, call data, and the signature. That's a lot, but let's see what is covered in message digest. So it covers source chain ID, blockchain ID, address this, good domain, also good nonce, token, and amount. But if we return to the relay function, we see that there is also target contract and call data, but they are not in the hash. So the validator signs of nonce, token, amount, but doesn't specify also the recipient. Recipient also never enters the hash. So the validator doesn't specify who receives tokens and which contract, with which data is executed. Let me show you what this may lead to. So what we do here. So the validator signs an attestation for Alice to receive 10 Ethereum, but an attacker takes this signature, sets themselves as the recipient, and submits vault release as a call data. If we go here and see the vault contract, there is a release function which is protected by only bridge modifier, and this is exactly how it will be called by the bridge. So let's try running it. Forge test match contract and match test. And let's trace it. And it passes, so validator signed 10 Ethereum for Alice, and attacker redirected it to themselves and even from the vault contract. So Alice got nothing. Here is what happened. The signed data included nonce, token, and amount, all good, but execute function also consumes recipient and target data, which are not committed to the hash. So the relayer controls the relayer controls this. Valid signature authenticates the message hash, but execution uses parameters also which are outside of the hash. So the result, unintended execution. So the validator authorized the amount and the token, but attacker chose where it went and which contract was called. Let me show you the fix. Here is the fixed version. So now the hash includes everything: source chain ID, blockchain ID, addresses, nonce, token, amount, recipient, target, and call data. Any change to any parameter invalidates the signature. Let's try running the same exploitation, but on this contract version. fixed. And now parameters forging is blocked. The signature now authenticates the entire execution intent, not just what, but who, where, and how. Here is the fix. Everything is inside the green zone now. Source chain ID, destination chain ID, this contract address, nonce, token amount, recipient, and payload hash. This step ensures that any parameter change invalidates the signature. So now execution is fully determined by the validator's signature. So here is the checklist for any breach audit. The message has which chain the deposit came from, destination chain ID, which chain this relator gets, address this specific breach instance, unique message ID, and anything that affects the outcome, full execution payload. For example, recipient, target, amount, token, everything. And if one of these are missing, the message can execute in the wrong context. That's an integrity failure. This is the audit principle for access to. The difference between relay parameters and the hash parameters probably means that you found a bug. So we have secured the trust boundary and message integrity. Now the next axis to get wrong, economic invariance. Here we will review fundamental accounting errors that violate the token's economic model. Firstly, we need to understand what is an economic invariant. Economic invariant is a property which should always hold true after every state transition. And it is usually defined by five main invariants. The first one is conservation. So total minted on the destination chains should not exceed total locked on the source chain. Solvency is the ability of the breach to allow users breach their tokens back. The supply cap means that the sum of supplies on all chains should be equal to the tokenomics cap. Like 1 million means 1 million on all chains, not on each chain. Accounting means each deposit maps one-to-one to exactly 1 mint. There are no double mints and no phantom deposits. And no free value means that there shouldn't be any paths to create tokens without locking the equivalent amount of tokens. So the bridge should only transfer value and not create it. Let me walk you through the common ways this invariance break. Let's start with the most devastating, which is supply inflation. So the project has a token with a cap of 1 million. And it needs to be deployed on free chains. So during deploy, they deploy it with the full supply on each chain. So even before any breach operation, the supply is 3 million, which is x3 times bigger than the required one. The tokenomics are broken at deployment, and this is more common than you would think. The fix is to native supply on one chain only, so on chain A. Every other chain uses a bridged representation, minted and burned by the bridge. So the sum of the supplies on each chain is equal to the defined gap in the tokenomics, always. The second pattern is misaccounting of fee on transfer tokens. Some tokens charge fee on every transfer. So let's say user sends 100 tokens and token takes two of them as a fee. So bridge receives 98 but records 100 and means 100. So the deficit is two tokens, which may look like not a lot, but multiplied by thousands of operations, and this will be a huge deficit. The fix is to measure the reality, not the assumption. So we don't take this value, we record what was the balance before the transfer, what the balance was after the transfer, and calculate this actual amount, record it, and mint it. So let's go to the third failure pattern, which is decimal mismatch. Some tokens, even if they are the same token deployed on different chains, may have different decimals. Let's say USDC have 6 decimals on Ethereum, but some its version might use 18 decimals on the destination chain. User deposits 1 USDC, and if the destination has 18 decimals, the received amount is just a nonce. Otherwise, in case it goes from here to here, 1 USDC will be minted to 1 trillion USDC. So either way, the invariant is broken. The fix is to apply explicit conversion. The bridge should know source decimals and the destination decimals. If source is 6 and destination is 18, multiply. Otherwise, divide. We had 3 bug patterns and 3 fixes. Now let me show you the first and most devastating one, supply inflation. But before we break it, let me state this rule clearly. For any token at any moment circulating supply on all chains, on chain A, chain B, chain A, should be equal to the token cap always. And if it ever drifts, this means that the bridge is broken. Let me go to the code and show you. So here we have the bridge, which has this token deployed on every chain, and in the send to chain, we see that it uses transfer from, and in the claim from chain, it uses transfer. So there are no burn and no mint here. So during these operations, it releases from a pre-funded reserve. So not using mint and burn operation, just moving tokens between wallets. Let's go to the invariant and check it. So we need to ensure that our bridge respects the tokenomics. We need 1 million tokens. Forge test match contract. Supply inflation. And it fails with 2 million is not equal to 1 million. So everything looked good here. Alice just bridged some tokens from chain A to chain B, but the inflation already existed at deployment because total supply across chain was 2 million instead of 1 million. Here is what broke. Before any bridging, chain A has 1 million, chain B has 1 million as well. After some breach operations, it still has 2 million total. So this is the inflation by design and made during the deployment, and it is also permanent. Let's go to the code again and see the corrected implementation. What we see now here in the send to chain, it uses burn, and in the claim from chain, it uses mint. And if we try checking the same invariant here, we need to ensure that there is only 1 million of tokens on both chains. And now it passes. So conservation holds, the breach only transfers value and doesn't create it. And also breaches are not pre-funded. So here is how we fixed it. Before breaching, chain A had 1 million tokens and chain B had nothing. And after breaching, the tokens were transferred between breaches, and the total amount of them was still the same as during the initialization, just 1 million. So the conservation holds and the supply is conserved. To sum it up, we can do some economic invariant checklist. From the architecture standpoint, we need a native token on one chain only. Don't deploy the full supply on each chain. There should be only one canonical deployment. Other chains should use mint and burn bridget representations, and they should have start from zero supply. The bridge should control mint and burn. There shouldn't be any pre-funded value that inflates supply, because if the bridge holds value to service claims, those tokens are also part of the total supply, and this is an inflation by design. From the operation standpoint, we need to check balance delta, not parameter, to implement fee on transfer securely and not to inflate fee on transfer tokens breaches. We should apply decimal normalization to ensure that tokens which have different decimals on different chains are bridged in the correct amounts. And two global invariants, which should always be true. The sum of circulating supply on all chains should always be equal to the token cap. And the second one is the bridged supply on the destination chains should be equal to the locked amount on the first native chain. So that's it. And we can go to the final axis. Now we've secured authorization, integrity, economics, and now we need to understand what happens when things go wrong, both on-chain and off-chain. If there are some bugs or if there are some operational problems. If validator is offline, if chain is halted, if a breach is posed. As auditors, we need to ensure that users still can recover their funds back. So the definition of liveness is the ability of the system to make progress and users to be able to refund their funds back. So there are three main questions we need to ask during the audit in terms of liveness. What if the relay never completes? What if the breach is posed? And if there is a possibility for users to recover funds without any privileged role intervention? There are three most common failure modes. The first is validator being offline. This means that no attestation is possible, which means that no relay is possible. Destination being halted. Relay just can't happen. And breach post may mean that new deposits are blocked, but existing ones have no escape. And all three of them may have the same result, funds stuck. Let's go to the first failure pattern. So validator being offline. User deposits, event is emitted, but validator is offline and no attestation is signed. So relay is just not possible. And if there is no refund function, those funds may be stuck forever. The next failure is the destination being halted. So validator is fine here. User deposits an event, validator signs an attestation, but the relay is just not possible because destination chain is halted. And if there is no recovery path, the same result, 10 Ethereum locked on the source. The next failure mode is breach being paused. For example, there is some security incident. Admin pauses the source breach, correct decision, no new deposits are possible, but before the pausing the contract, some Ethereum was deposited. And if there is no recovery path for them, they are also locked and may be locked forever. In all three cases, the same missing piece, no refund mechanism. Let me show you how it may break in the code. So here we have the breach destination again. If we go to the message digest, we see that the breach has versioned message format. Version 1 has minimal hash, recipient, amount, and nonce. V2 has full domain binding with blockchain ID and address this. Admin can upgrade it via upgrade message version, and this upgrade improves security. But look, when this version changes, message digest immediately changes the formats it accepts. So if user deposited before the upgrade and validator signed version 1 attestation, that attestation will not go through this function. This will be rejected and funds will be locked on the source forever. Let me show you. So what we see here is that that Alice deposits 10 Ethereum, this message is signed and is successfully relayed on the bridge. Then Alice deposits 5 Ethereum again, and it is signed as version 1 message. But then admin upgrades the contract to the version 2. And when relayer tries to submit these really deposited funds and signed by the validator message, it reverts. Let me show you. Forge test. Match contract. Upgrade in flight vulnerable. And let's trace it. And it fails with invalid signature. So Alice attestation was valid before upgrade, and there was a real deposit, but admin upgraded it to the version 2. And the same attestation is now rejected. And this in-flight message is now stuck forever. How to fix this? The first thought may be just pause the breach, then upgrade. But what we need to pause? Deposits happen on the source chain. If we pause the destination, the funds will still be locked on the source chain. So we need to start from the source breach part. Let's go to the breach source, and we see three main functions here. The first is deposit. User submits Ethereum, nonce is incremented, stored, and pending count is incremented. Then there is a mark relate function protected by only owner modifier, and owner confirms the relay landed on destination, and during this pending count goes down and message is marked as relate. And refund. It is only possible when the contract is paused and can be called either by the depositor or the owner. It cannot be done this way because in case only the depositor can refund, this may lead to the Griffin attack when only one depositor may block the whole upgrade. So during the refund, refunded field is set to true and pending count also goes down. So this is the escape path. During an upgrade window, users don't lose money, they get refunded. So now we need to go to the destination chain, and we see that in the upgrade message version, it is checked whether the contract is paused, and it can be upgraded only in case it is paused. So the contracts need to check what they can, but due to the fact that this is cross-chain interaction, it is also an operational procedure. So the full safe upgrade procedure is firstly to pause the source, to refund all the pending deposits. After that, pause the destination, upgrade the message version, and unpause both. So the contract enforces what it can, pauses before upgrade, and the cross-chain coordination is the operator's responsibility. That's realistic, and real breaches work this way. Let me show you this secure procedure here. So Alice deposits 10 Ethereum on source, relays it, it works fine. Then owner marks this as a relate on a source chain. So it cannot be refunded. So because it was relate. Then Alice deposits 5 Ethereum on source chain with nonce2, and admin needs to run an upgrade. So admin stops, pauses the source chain breach, refunds the pending deposit, and pauses the destination breach. After that, upgrades the destination breach and unpauses both. And now there are no blocked funds. Everything is refunded and everything is upgraded securely. Let me run it. Forge test match contract upgrade in flight fixed. And now it is fine. So here is what happened in the broken version. User deposited validator signed an attestation with version 1, but the admin upgraded message version to the second one. And this valid attestation was delivered to the destination bridge, but was not accepted because version hash was not the current one. And as there was no recovery path, then Ethereum were locked forever. And here is the safe upgrade procedure. In case we need to pause the bridge, here is the pause part. We need to pause the bridge source. All the new deposits will be blocked. We need to refund everything, and when pending deposits is equal to 0, we can pause the destination, upgrade it, and unpause both. Then no funds lost, and the upgrade is safe. So the key insight here is this is an operational runbook, not just a single cross-chain call. The contract enforces pause before upgrade, and the rest is the operator's responsibility. We can do some checklists here as well. From the timeout and refund perspective, each deposit must have a recovery path if relay fails. And the timeout for it should be long enough, and refund should be blocked after the relay confirmation to avoid double funds receiving. Regarding the access control, the refund should not require admin or validator action. It may allow admin or validator action to prevent griefing, but also original depositor should be able to claim the refund. And pause should block new deposits, but should not trap existing ones. Regarding the state machine, each deposit should have a terminal state. It is either relayed or refunded. There shouldn't be state where funds are stuck with no exit, and state transitions should be irreversible. So a relayed deposit cannot be refunded, and refunded cannot be relayed. And the one we demonstrated live, upgradability. Upgrades should follow the secure sequenced procedure. It depends on the architecture. In our case, it was pause, drain, pending, upgrade, and unpause. There shouldn't be no instant format switch when there are some in-flight messages, and contracts should enforce what they can. So, for example, they cannot upgrade some format if pending count is bigger than 0. And for the upgrade safety, there should be a documented migration checklist for the operator, which their operator should follow. And that's it. So if you have any questions, feel free to ask them. Also, feel free to explore our website to learn more about our services. With 5 years in the market and over 1,500 clients, Hacken is your blockchain security partner. We provide a continuous security approach, combining audits, compliance, and monitoring. And if you have any request, want to learn more about Hacken services, have any ideas for cooperation, please scan this QR code to connect with a Hacken representative, and Breen will be happy to answer all your questions. So, in case there are no questions, I believe we can end the session. And thank you for attention, and see you in the next